Evaluate each of the following expressions and give reasons for your answers. A, integral of derivative of square root of ln of x squared plus 1 dx. Okay, so this is an easy problem if you know what you're doing, and quite painful problem, I guess, if you don't. So hopefully we know what we're doing. We're trying to find first the inside part, right, the derivative of all this. Okay, so just imagine, don't do the details, but imagine taking the derivative of this. We'll have chain rules aplenty, right? Power rule, half comes down, subtract 1, blah, blah, blah. So we get just some messy thing by taking the derivative. And then whatever we get, we take the integral of. So we now have the integral of this messy derivative calculation that we just finished. But look, the integral symbol just means find an antiderivative, right? And so whatever derivative stuff you ended up with here, when you do the antiderivative, you're just going to get right back to this guy. And so the answer to this problem is just this guy, almost. So this is equal to square root of ln of x squared plus 1. Almost full credit, we're just about done. So when you do the antiderivative, that symbol goes away simultaneous to this. So you definitely don't need to put like a dx over here. That just disappears. But one thing we do have to take into account is that when we, in our heads, took the derivative of this guy, and then imagine taking the antiderivative, well, this symbol right here means general antiderivative. And so if you imagine like the messy thing that would have come out of this derivative, you do all your antiderivatives and you get just right back to where you started, but then the general antiderivative has to have something right here at the very end. Easy to forget, especially in this problem. Plus C is our final answer there. Part B, derivative of integral from 0 to the square root of e of the square root of ln of x squared plus 1 dx. Okay, this is kind of a sneaky question, but really easy if you catch the trick. I'm going to temporarily ignore this integrand. It's just some complicated function. And I'm going to recognize that when I have a definite integral, that is an integral with numbers, 2 limits of integration, then ultimately that entire calculation underlined in purple is a number, right? It's not a variable. It's just going to be some number. I don't know what the number is, and frankly, I don't care. I'll bring the function back. I don't know what the antiderivative of this thing is. It looks quite complicated to me. But whatever it is, we would just plug in the top number and plug in the bottom number and subtract, right? And we would just get these two numbers subtracted from each other. So ultimately, this entire thing in the parentheses is a number. So this is saying find the derivative of some number. Now that number is really hard to find. I don't think that I could find it, to be honest with you, but it doesn't matter because we're taking the derivative of it. And what is the derivative of any number? It is 0. So the answer to this problem is 0. Part B, derivative d du of the integral from pi to u of that same square root function. Okay, so this now is something that's different. This is the integral from a number up to a variable. This was from a number up to a number. And so if you saw this form and you said, oh, good, that's the fundamental theorem of calculus, well, you were on the right track. But the fundamental theorem of calculus has a very specific form that looks almost but not quite like that and does look an awful lot like that. So I'm just going to go a page back because I've written this fundamental theorem on a previous problem. It's right there in blue at the top. So the fundamental theorem says, if you happen to take the derivative of something that looks exactly like this, that is the integral from any number up to x of any old function, dt, then in a very real sense, derivative and integral cancel. Integral sign and the dt go together. So everything just disappears in this big explosion. And all you have to do is take the variable, which is this t inside, change it to an x, and you're done. So the derivative of this particular form of integral is just equal to h of not t, but x, whatever is up there. Wonderful. So how do we apply that to part C? That we can, because it looks exactly like the derivative of the integral of some number up to a variable, that variable same as up there, of some function which we don't care about. And so the fundamental theorem makes this problem trivial. All we got to do is go right inside of this function. And any place we see an x, which is just one single place, we change it to that letter, which is a u in this problem. And so our final answer to this one, this problem's over before it begins, is the square root of ln of, but it's not x anymore, it becomes u, still squared, still plus 1, the dx, the integral, the d du all disappear in that big explosion, and we're done. Part D. d du of integral from 1 up to sine of u of the function we are tired of looking at. So this is kind of the same as part D, as part C, right? It's again, it's got exactly the right form for the fundamental theorem of calculus. Derivative of some number up to, okay, it's not quite u, it's a function of u. That doesn't really bother me too much. And then whatever function is here. And so what we're going to do is exactly the same thing. I'll underline it in the same color. This function right here, all we have to do is replace the single x, any x that you see, there's only one, with whatever was up there. So what was up there in this case wasn't just plain u, but rather was sine of u. But the calculus doesn't care. We're just going to copy it just as it is. So this equals square root of ln of, but instead of x, it becomes not just u now, but sine of u. All right, then that guy, whoops, sine of u, and then that thing is still squared, and there's still a plus 1, and the dx and the integral and the d du, again, all explode and disappear. I'm missing some parentheses somewhere. Here. Still missing parentheses. What's going on? No, okay. I guess we're good now. Right. Okay, and so we're almost done, but then there's just this little twist at the end that says, okay, if you happen to know the formula, the way to take a derivative for a u, or just a plain old x, then it's exactly the same rule when it's a function of u or a function of x, but all you got to do is let the chain rule come in. And after you've applied the basic rule, like we pretended this was just u, and we just treated the problem like it was a u, but then the chain rule says, hey, but you got to pay for it, and the price isn't very big, but you got to multiply by the derivative of the stuff. And so that stuff, let's go purple here. So this is the stuff. And so the derivative of the stuff, derivative with respect to u of sine of u, is cosine of u. And that is what we need to multiply by, cosine of u. That's the derivative of the stuff. Otherwise, the chain rule says just do the normal thing, but then just stick on the derivative of the stuff at the end.